talk there is what is a geoscientist to do in an era of unlimited oil and no exploration. So kind of thinking about that, well, one of the things that we do in tough times is kind of try to add value through existing fields that we have. Okay? So let's kind of go through what I wanted to cover today, the objectives. So one of the things I just wanted to go over is what are the types of opportunities that we typically find within existing fields. And I'm going to be leaning in this talk more toward fields that are more mature. And the other thing to look at is what is it about reservoir description that is particularly important for optimizing field development and explaining how to spot previously unrecognized opportunities within our fields. And then kind of thinking about the types of activities that would generate new opportunities, and then talk a little bit about new and evolving technologies and how that is related to finding new opportunities. And so those are the things we want to kind of accomplish in today's presentation. So kind of the motivation behind this is a little bit our subsurface leader, Mason Gomez, asked me, we were talking about geosciences in general. I am the technical director of Geoscience. That's geology, geophysics, and petrophysics for Petroskills. And we're talking about, with the slowdown, kind of what are geoscientists supposed to do, those particularly that are involved in exploration. And so kind of my motivation is kind of what are the things that we can do in times when prices are a challenge. I teach 2 classes and the course director and originator of a development geology course and a course called Integration of Rock Logs and Test Data, which is based on my own experiences in those fields and a lot of consulting over my career. This presentation comes from material in those classes and also from 2 papers. One I wrote, which is now almost 20 years ago, New Oil in Old Places, which looked at about 82 fields that we acquired and what was the potential on those. And I've recently done an update of that paper that's in press right now. Both of these are going to be in our AAPG memoirs. And we were looking at adding new reserves in production in giant fields, and what else have we learned in the last 20 years about field acquisition and redevelopment. Okay, so that's kind of where the material comes from and thinking about what do we do in this environment. I've spent a lot of time both in appraisals and in redevelopments. Okay, so what I wanted to do first was kind of look at key elements for adding reserves to our fields, and then the type of opportunities. That kind of set the stage, and then we'll spend the majority of time looking at what is it about geological characterization of our reservoirs that helps us find these new opportunities. I've got a couple of short examples depending on how we're going with time, and then a quick wrap up. The picture on the right there is Signal Hill, which is in Long Beach, California. And I put that up there as this is a field that was more than 100 years old, and it's still going, still lots of hydrocarbon being produced from this field. So we can still find a lot of hydrocarbons in old fields. The question is, can we do it economically? Okay. So looking at the introduction, every field has hydrocarbons that haven't been realized or undiscovered, and most of them have some amount anyway. But that doesn't mean we can produce those hydrocarbons economically. Okay, so we have to look at that. And the economics is one of the critical parts, and obviously prices play a role. We need a very good model to work on. It's critical that we have a good understanding of geology. However, that's a real difficult thing to balance because we can't do every single thing that we can think of. We have to be conscious on what we do. So we have to be very strategic on how we apply our time and our money and technologies. Okay? So we have to think about that aspect. Technologically, the new technologies can't create hydrocarbons where they don't exist. Sometimes they're very expensive. So we have to apply them in areas where we think we have the greatest potential. So technology is part of the equation, but it's only one part, and not the biggest necessarily. It depends on the project. A key thing is to kind of be systematic and strategic about what we do and how we study them. And we can decide not to do things, but we have to think about why. Okay. So in the latest paper that we wrote, we did a lot of thinking. We read probably 100 to 150 papers, plus based on our own work, and started reflecting about kind of what are the key elements required based on all these things that we looked at to kind of add hydrocarbons to the reserves. So we identified 3 major elements in all the papers read, 1 or more of these things that they did. First thing is, inaccurate characterization of the field, and I'm talking more on the geology side, leads to missed opportunities in the field, or our development plan isn't optimized because we don't have the quite right model, and in some extreme cases, economic failures of projects. Now, in the hindsight, in fields that we have, recognizing these mistakes can lead to large upsides. And I don't want to say that people did anything wrong initially, but again, we don't have all the information we need, and over the life of the field, we learn a lot more. So many reserves were added by just improved characterization of the reservoir, improved understanding of the reservoir, okay? The other thing that we saw is new technologies allowed us to do things better or differently, and we'll talk about the aspects of that a little bit later on, but there's all kinds of things from visualization improvements, production, and then of course drilling and completions are the main kind of technologies, and we'll discuss those a little bit more detailed later on. And then the third thing is one that's a little bit harder to put into kind of words, but it's more innovative thinking, using non-traditional strategies, thinking about or recognizing things that other people missed, maybe unorthodox applications of techniques or technologies. And then one of the things that was kind of interesting is a lot of extra hydrocarbons have been produced from mature fields by having kind of unique financial fundings and strategies. So that's something we probably don't have the time to get into a lot of that, but I just want to mention that. Okay. So many successful projects incorporate all 3, and you could argue that at least number 1 and 3 are critical in most mature field redevelopments, and technology may or may not be part of the solution. It just all depends. So if we kind of take a little bit of step back and think about where do hydrocarbons or new hydrocarbons come from in mature fields, this diagram comes from the 2001 paper, where this is a summary of some work we had done over about 15 years, 10 years. And this is from 82 fields that we studied and multiple projects and some acquisitions. We looked at fields that had primary potential for primary recovery, and those that had IOR as enhanced oil recovery, or sorry, improved oil recovery, and then EOR as enhanced oil recovery, and I can talk about the differences later if we have time. But so in these 82 fields, the 2P reserve numbers we ended up with was about 625 million barrel of oil equivalent in these fields that were late in their stage of life. And that's a very large number, but if you divide 625 by 82, we're talking about maybe 7 million barrels per field can be added. And these were fields of all different sizes. Okay, so that's a pretty big number of things that we saw. So kind of looking at the types of opportunities, workovers, so zones that aren't producing that should be for mechanical reasons often, bypass pays that weren't recognized or zones that were then recompleted. For us in the economics of the projects we run, which we're not going to get into economics in this talk, these have by far the best return, and when prices are low, these are one of the best things to do. Simply going back into a borehole and perforating zones that weren't recognized in the original development. Okay. So that's about 25% of the hydrocarbon potential we found, and this is in fields that only have primary potential. Okay. Better visualization of the reservoir or a better reservoir model led to a lot of opportunities in either infills or extensions around the field. This is a bigger volume of hydrocarbons than we saw in the bypass and the workovers in bypass, but its economics is poor because you have to make capital investments. But again, so when price sensitive, it may not be as economic as doing these easier bypass things. If we add water injection and other types of enhanced oil recovery, miscible floods and heat and things like that, we saw in those fields about 40% increase in recovery based on putting those processes in. However, these have poor economics because it costs a lot of money to inject fluids, and I'm not saying you can't do it now, but it costs more money, and they always have a lower rate of return because there's a delay between the time that you invest the money and the time you see the increase in production. So they're just kind of, what are the kind of things that we typically see? So what I want to do now is say, okay, here's kind of the opportunities that we see in the field, and how does that translate into the geology, or how do we find those things, and how do we put the geology that we describe into that context where we can understand and find new opportunities. And so this is kind of it's a basic flowchart that I use a lot of the times that kind of helps us think about different aspects of the geology that control production in the fields. And so these are the key reservoir description categories I have, and we'll talk about each of these. And when I go through this, I just kind of think about, well, or I'll try to point out as well, what do each of these topics tell us about the reservoir? Okay, how's that reservoir going to behave? And then, when we're going through and thinking about the reservoir description, how does it impact the development plan? So how does the geology affect the well spacing, the number of wells, how the reservoir energy is going to behave over time, the rates of production we have, our ability to describe it petrophysically or our petrophysical, and I include in petrophysical geomechanical properties, and then how we're going to document those reserves. So, and kind of add into that, that's just general things that we think about, but how might better understanding these lead to redevelopment or opportunities in existing fields? Okay? So as we have a better description, what can we add? All right. So in the geological setting, I'm talking about a little bit larger scale. I won't spend too much time here, but just a couple images to kind of give you the idea of the structural setting that we're in, and some typical things here that are important, certainly in development and appraisal, can be the stress regime. And I put stress regime here. It's related to the overburden, pore pressure, and in the differential horizontal stresses. And this is important for certainly deep water, also if we're drilling horizontal wells, and if we're working in any tight reservoirs, the frac design and all that is linked to those differential stresses, and all that is important information for us to know. Okay. Some of these other things are also critical, but not as important for what we're going to talk about today. Going down to the next kind of topic in our characterization is what I call external geometry. And what I'm talking about here is the shape, overall shape of the field, its orientation, its basic structure. It's made up of two parts, the structure itself. So we're talking about the faults, rollover, all these kinds of basic things, the basic thing that defines the field. And it has a major impact on what happens. Very important component. The second component is the stratigraphy and the external geometry. So this is our major reservoir packages, major unconformities, major through-going shales, which I refer to here as floodings. Those are the big things that control the overprint of how the field can behave and set its limits. And that's incredibly important in our appraisal development, tends to have less drive in redevelopment. Okay, so external geometry is the container, internal geometry is what fills it, and we're really talking about, to a large extent, how continuous is the reservoir? What is the continuity of the reservoir in the trap or whatever it is? Okay, and so this probably is the one that's one of the more important ones that leads to additional opportunities in mature fields, things that aren't as easy to recognize in the initial development plan. So small-scale faultings is a very large driver for bypassed zones and fields. And so when we're thinking in exploration, we think about the big faults, the ones that trap the hydrocarbons. But in this little map I'm showing you here, I just put this up here. Here's the main bounding fault. Let me get a laser pointer. Kind of the main bounding fault for the field is kind of in here, and these are really big faults that I'm kind of highlighting in here. But there's a whole bunch of small faults internal in this field that were actually not mapped for the first 30 years of this field. They weren't really even, they may have seen them, but they were small faults. But these small faults create incomplete drainage. And the area 4 there to the south, well, this field was put on production in after 25 years or so. When we went in and restudied this, we found out that these small faults in the neighborhood of 10 meters were kind of damming hydrocarbons up here. And we ended up being able to recommend a series of wells down dip. So while the wells up here were dying, we were able to add about 40 million barrels of hydrocarbons just because of this poor, incomplete drainage or partial completion or partial connectivity to the upper part of the reservoir. Okay, so I think that faulting is kind of rather obvious the way it can lead to this, but it leads to a lot of additional hydrocarbons. So what are the more major drivers? There we go. So the other thing that we find in mature fields that isn't often recognized early on is kind of vertical barriers within the reservoir packages. And to the right here of this map, I show a cross-section that's from the same field. And, you know, originally this was broken up into major packages. This is pretty sandy. But what we found through studying the pressure data in this field and looking at the geology is each of these sand packages is really subdivided. And this is a mass of sand if you look at the gamma ray, but if you look at the resistivity, you can see these variations in resistivity. Hopefully you can see that. Those are actually breaks of shales that are subdividing the reservoir. They're fairly thin, and they are effectively isolating the reservoir vertically. Same thing up in here. This was considered one reservoir. And again, but when you look at it, you know, this well was an appraisal well that was drilled, or sorry, development well. And it was depleted in the lower half of the sand, and the top of the sand was at original pressures. So when we perforate a zone, we often don't perforate the whole interval. Maybe we're afraid of water or anything like that. Maybe we will frack it, but what we see in a lot of these fields, when we go back, we may not have effective drainage. Okay? In this case, somewhere in 20 to 30 million barrels, we identified for redevelopment targets just based on those kind of small, thin barriers isolating the field. Now, another thing that we're going to start seeing, I think, even more of is not just barriers to fluid movement, again, which is by low permeability rock separating the reservoir, often below log resolution, but there's also barriers to our fracture stimulations. And this diagram I added is just looking at a fracture model to the right, and then kind of the frackability on the right, on the left plot, looking at how easy it is to fracture layers. And so we're going to see a lot of this in the unconventionals and even in our conventional fields. And a lot of deep water work I've done, we've done the fracks, and we found that they aren't effectively connecting across barriers, so they can be stimulation barriers as well. Okay. Other things that we won't get into, obviously, that are part of the internal geometry, the thickness, H stands for thickness of the zone for what's pay, and natural fractures are important as well on some projects. Well, let's look at a example here of small faulting that is actually below seismic resolution and how it affects or creates opportunities in the future when we understand it a little bit better. So this is the Beryl field, which is located in the North Sea. It was a field that was very well developed in its initial phase of life. And so I think, you know, it's not like people made mistakes or anything like that. It was a well-developed field. But as it declined, the major, which is BP, did a great job developing this, no problems with it. It was no longer a core asset for them. And so they sold it, and another company that was smaller with different criteria, Apache, bought it. And so with a new operator, there was new ideas, and they did an active redevelopment plan. They took new data, some broadband 3D, which helped, but not as much as one would hope. And they had new economics, and that was one of the bigger things. So new ideas and new economics. They could go after smaller targets that was meaningful to a company that wasn't the major. But again, it all depends on, you know, lots of majors do these things as well. So the initial development of the field targeted 3 reservoirs. So let's look at the geology a little bit. We have the base Cretaceous kind of unconformity right in here. So Cretaceous age above that red line, and then below this is Jurassic in age. This fault right here is this major fault right in there. And then the reservoir itself is subdivided into 3 separate reservoirs. The Barrel 3, which I'm highlighting on that image, the Barrel 1, and then the Lenny Reservoir. So there's 3 separate reservoirs stacked here, and of course internally they're also a little bit more complicated. Okay. So this fault block was originally developed by this well B34, where that red arrow is, and it produced 4.6 million BOE, barrel of oil equivalents, before it was abandoned. It was abandoned in 1998 because it had a high gas cut, and so they didn't have the ability to handle that on the platform. So kind of looking at that, looking at the decline curve analysis, Apache came up with a target of about 3.3 million barrels remaining based on the decline curve from B34 if you had the ability to handle increased gas cut. So what they expected to find was that the Barrel 1 and Barrel 3 would be depleted, and that the Lenny wasn't very well drained, or wasn't drained at all in the initial development. So they targeted that well, and when they drilled it, they had a bit of a surprise. So the Barrel 1 was not depleted, it was at original pressure, and then they found that there was a number of separate fault compartments within this block that they thought was contiguous. They had 7 new faults that were mapped, but we talked about the new seismic data, but the seismic data wasn't, even the best seismic data wasn't quite good enough to resolve these. So using well data with the seismic to help, they found 7 new faults. They knew that they might be surprises there, and so they were flexible. They ended up drilling 4 new wells. The EUR was about 10 million barrels from the original 3, and that's what it's produced through 2018, which is the last data I have on that field. Now, that's an example, but how would you find this? Well, if you did a study, and what I typically do in these, if you did a proper reservoir study, you would calculate the EUR from the decline curve, and if you use the geological model and the volumetrics, you would see that something was wrong, that the recovery factor for that block was too small. And I'm sure they did that as well. So we know that we have to question what's going on. Something's wrong with our model. And so that creates opportunity. So that's 10 million barrels to add in something that was abandoned. So just kind of a quick example. Okay, so the next major category when we're characterizing and building our geological model for the field is to look at the pressure distribution and the fluid distribution. And so when we're doing the original development of the field, some of the things that are kind of most important are viscosity of the fluid, FV, F stands for formation volume factor. We need to understand how it's going to change when we start producing it. And of course, the composition and impurities of the fluid are critical for our initial plan. As we start looking back, one of the things that we see a lot in the fields, and I'll say misunderstandings that lead to new opportunities, are understanding how the different columns might be connected in a reservoir that's not homogeneous, which is most. And so we have to look at how many, if we have a multiple stacked pay, are they in the same accumulation? Are they separate accumulations? And we see a lot of misinterpretations early on where they end up being separate. And then even if they are in the same, what we'll call accumulation, so this is kind of showing 2 layers here on the first part of the diagram, and below it, we're showing kind of a pressure gradient where all the hydrocarbons are on the same pressure gradient. And we often say that means that they're in communication, but what we find is that even if they share the same seal, which means they have the same pressure gradients, that during production, if permeability layers are low within the stratified column, we see a lot of poor drainage. So understanding vertical connectivity and even lateral connectivity is one of the things that we see in mature fields where we can find new pay opportunities. Another one, which is, if you're not familiar with this, a little bit more complicated to understand in just one quick slide, is Looking at kind of the individual fluid properties of each rock, its saturation height function, and let's just say identifying the types of contacts that we see. So if we look at this middle diagram here, we have capillary pressure, again, which is equivalent to the pressure differential between the two fluid phases here. And then this is a plot of saturation versus this capillary pressure for two different rock types. This lower one here has a lower irreducible water saturation, the one here higher. And when we talk about fluid contacts in fields, we typically talk about a single contact. And the reality is we have to break it down into a multitude of contacts. And I'll show a second example here in a minute. But so typically what we see is each rock type follows its own saturation height pattern or trend. And so we need to identify where the free water level is. Again, free water level is the intersection point here for the pressure gradients. And then we have our kind of where hydrocarbons first occur in the rock, but at high water saturations, and then we have to find where the hydrocarbons actually start producing. And this diagram here is meant to show the difference in behavior between these two rocks. And so when we draw in a fluid contact and where we can produce it, so let's say the light green here is what we can produce economically without too much water cut, where that is in the field changes by rock type. Some other things that are part of this is related to source rock maturity and viscosity. That's mostly for unconventionals, and I won't talk about this right now. All right, so let's look at so what. I mean, I kind of think it might be a little bit easier to understand what I was talking about here. This is a mature field, been on production close to 30 years. It's a large gas field, reserves over 1 trillion cubic feet of gas. The sandstone here, this is in meters. It's about 200 or more than 200 meters thick. There's a 100-foot scale right here at the bottom of that for you. This reservoir was interpreted to be relatively constant. Porosity here around 23%. So kind of all big stack sandstone. Everybody thought it was homogeneous for the most part. And what you notice quite distinctly here on these curves, on the left, this is a SP, and to the right here, this is our normal resistivity curves. And so we have our highest resistivity here. The blue is the deeper curve. The black is the shallower resistivity curve. And let's just focus on those two for now. And what you see here is the deep resistivity is higher than the shallow, and we have a real steady decline in resistivity. They picked this as the original gas-water contact for the field. Thinking this is maybe transitional, that's what they put as the kind of producing contact for the field. Well, they produced it for 20 years. The data never matched, the production data never matched the geological model, all kinds of problems in the interpretation of it. And we looked at it kind of later in its life, and we're looking for different opportunities. The first thing we did is kind of looked at the cores, and what we saw is that this is not homogeneous. Even though it has constant porosity, it has a very large change in grain size from very fine grain to medium grain. And as that grain size changes, so does the permeability. So permeability is greatly affected by the grain size of sandstones. And so we see actually 4 distinct rocks in here that had permeabilities that range from 2 to 2,000 millidarcies. Again, so what? Well, if I break this up into the rock types, A is the rock with the highest permeability, about 2,000 millidarcies. D is the lowest permeability rock, which is about 2 millidarcies, which would be reservoir quality for gas. We can see that the resistivities are in many ways following the changes in the rock type. Now, how does that occur? Well, one of the things that we would do and what we did in this field is we built a saturation height model from capillary pressure data. And look, these are the capillary pressure curves, so the saturation versus height above the free water level for each of the rock types. And what we see is A has the highest permeability. It also has the highest resistivity. Right? Why is that? Well, resistivity is a proxy for hydrocarbon saturation or water saturation, both. So the idea is the more hydrocarbon the rock, the less it conducts electricity. So we have, that's an indicator of hydrocarbons. As we go into lower quality rock, we can see that we're going to have higher water saturations. And so what we're following here is a combination of height above the free water level and rock types. So we started A right here at this depth. We're in a high quality rock. If you notice here, we have resistivity with the deep higher than the shallow. We get down here, we get a resistivity inversion. And this is basically the free water level and very close to the gas water contact. As we start going up above that, we go into rock type A, which has high permeability. So we get pretty low water saturation here. As we go upwards, the rock quality decreases. So we go from C to D. We have a lower hydrocarbon saturation, therefore the resistivity goes down because there's more water in the rock. And then as this is a prograding wave-dominated deltaic complex is what we've interpreted it as. So as we prograde and fill the basin, it gets coarser grained. And so we're now going toward these better rock qualities. And we're decreasing in water saturation because we're higher above the free water level and because the rocks have higher permeability. We go up here higher, the rock quality goes down, and so the water saturation increases, which we're seeing in the change in resistivity. Okay, so if just a couple images here, this is rock type A, it's medium grained sandstone. These are at the same scale. This is rock type D, it's a very fine grained sandstone. And the reason these rocks are behaving differently is tied to the differences in grain size, which is tied to the depositional environment. Okay, again, you might be asking yourself, so what? Well, it tells us that our gas contact is 100 meters lower than we thought it was. Okay. So let's put this in a kind of a schematic cross-section view. So here's the well log. Here I've put some colors on it. It's at the same scale. This is the free water level. And so essentially the darker red color here is the producing hydrocarbons, where water cut is low enough that we can produce it economically. The light pink is in the transition zone where we have a mixture of gas and water. And what you can see is the original gas-water contact is up in here, but depending upon the rock type, we can go significantly down dip and still find producible hydrocarbons. Now, the question is whether or not we drain it from the wells that are above this original contact, and that's related to connectivity and permeability. But again, we added to the in-place numbers 40% more gas in place just by changing where the real contact was. And that led to a series of ideas for us to chase down for redevelopment of this field. Okay. We see this in oil fields. It's even a bigger change based on rock type. So these variations in vertical thickness are less with gas than they are with oil. So again, this is a very common thing that we see in old fields. They early on draw a producing contact for the field, maybe because they want to have low water cut, but sometimes we see extensive hydrocarbons that haven't been developed in the original development, and people haven't gone back and thought about, well, where is the real contact in this field? Okay, so kind of the last of the kind of key descriptors in our reservoir model are what I'm calling the petrophysical properties here. And this includes things that are porosity, permeability, water saturation, mineralogies, kind of how the logs might behave. Also the geomechanical properties I included in here. But there's two things I want to focus in on that lead to finding additional hydrocarbons in our fields. Okay, the first one is, I kind of touched on it earlier, the thin barriers that have low vertical permeability that might subdivide a reservoir. They're also in petrophysical properties because sometimes the log resolution is not sufficient to properly image the reservoir, so we can have thin beds of sand and shale intermixed which are hard to recognize. And another one that leads to a lot of missed pays is if we have rocks with different properties, mostly irreducible water saturation. Well, what we define as pay originally in the field might bypass a lot of hydrocarbons, okay? So I'll explain both of these here a little bit more, okay? So the last bullet point over there is this LRLC, which is kind of stands for low resistivity, low contrast pays, okay? So we're gonna look at this log here in a second, but before we do that, I wanna talk about why do we miss pays typically in fields, or why we might not produce them originally. So one of them is because of the zones might contain a high irreducible water saturation. And again, we use water saturation as a cutoff for pay, but it's not uncommon to have 60, even 70% irreducible water saturation. So the better rocks typically have a very low water saturation value for irreducible, but we can have pay zones that look wet at 60 or 70% water, but will produce water-free. That's one that's quite common that we find. The other one I mentioned a bit earlier, which is thin-bedded, and it's below the resolution of the log. So this is our thin-bedded resistivity problem that you often hear about. Okay. So another problem we might have is that the rock itself conducts electricity. So just because a rock has shale doesn't mean it conducts electricity. And then another reason for missing things is because the rock is tight or tighter than we conceive to be productive, and so we don't complete it. The extreme case of that is unconventional reservoirs, where we've unlocked them with new completion techniques, but it doesn't have to be that extreme. Now, just to kind of come back to what is conventional pay, well, typically we think of conventional pay as having high porosity, high resistivity, and low gamma ray equating to low clay content. So if we have rock that has the lower resistivity because it contains more water, we might miss that zone. Before we can talk a little bit more about some of the examples, let me just review with you kind of clay distribution of rock, or even shale distribution, the subtle differences between the two. Shale is a rock and clay is the mineral. So clay can be, or clay and or shale can be distributed in rocks in a couple different morphologies. And this plot here shows that. So it can be laminated, it can be kind of filling the pore system that's typically dispersed. It can be diagenetic, lining the surfaces, class of shale, clay-lined burrows, and clay grains, which means the grains typically contain lots of microporosity. So we think about the clay and the rock, and it can have different distributions, and these can lead to misinterpretations. Okay, and again, we have we cover this quite a bit in ILC. We have a whole 5-day training course in shale sand equations, or shale sand reservoirs APS, that talks about how to do this. So we're doing it at a pretty high level. A lot of people think low resistivity pay means laminated pay, but there's lots of other types. So let's go to this example right here. This is part of our 2001 paper in a field that we were involved in acquisition on. And the original pay was that upper zone with high resistivity. Let me just, my pointer's not working right now. I'll have to do without it. So that upper zone with a high resistivity was the conventional pay in this field. Now this is one of multiple pay zones in the field. This field was put on production. That upper high resistivity zone was produced and eventually watered out, and this was abandoned. However, the zone before, this field was actually purchased for this interval right in here. Okay. So in this interval, you can get by the nature of the gamma ray that there's a lot of variability. So this is thin-bedded sands and shales. And in addition, the sands have dispersed clays filling their pore system, so the permeability is less than it is above. But this zone, from basically where my pointer is now down to here, contained about 14 million barrels of reserves that were produced. So the upper zone this is a 30-day test in the upper zone, it can produce about 3,000 barrels a day. That's the best pay in the zone. These are individual flow rates from these smaller zones. They're less, but they add up to about 1,000 barrels a day. So in this field, this was one of 28 horizons, basically came in here in the first year of after acquisition and just perforated all these zones in a series of wells and, added a significant amount of production in 14 million barrels of oil without drilling a single well. So this is something that is particularly good in low price environment because you don't have a lot of capital expenditures. Well, I wanted to show you one more example of kind of this unconventional bypass pays that has a totally different mechanism. Okay. So in this field, if we kind of look at it, this is 10 meters right here, kind of for scale. This is in feet on the scale here if you can see it. So we've got this interval here. It's sandy. It's considered one sandstone. If you look at it, you've got resistivity increasing to here, then it drops off, and then I've got a zone of lower resistivity. This was considered and identified as pay in the field, and actually this zone wasn't deemed to be big enough because it had a very small oil column in it to be developed. Okay. However, what the operator did is they actually collected the data with wireline pressure testing, and they collected some sidewall core samples in here so we could see what was going on geologically. And let's just say, to make it clear here, this entire interval is productive and there is no water-bearing intervals in here. They tested this upper zone, it tested about 4,500 barrels a day, and the lower zone produced about 1,000 barrels a day. So what's going on here is quite simple. Actually, we have here is immature grains, meaning, rock fragments, feldspars, things like that are not stable in subsurface in the reservoir conditions, and they've altered to clay or created abundant microporosity in the grains. And so you've got hydrocarbons in the zone that's blue here in this diagram. You've got water held in the grains themselves. The water is held tightly by capillary forces and can't produce. And so what we're seeing here is a dual pore system, which is part of the water is in the grains, and then the pores themselves are full with hydrocarbons. And so this whole field here is charged with hydrocarbons. This was too small to be worth developing originally. Now this zone is an economically viable target. These are things that we see on a regular basis in many fields. Okay, so that was kind of the meat of what I was going to present here in talking about kind of just checking the time here, kind of what is the main things that we see. And so to kind of look at the rest of it here, kind of what are the elements that bring us to technological advances? How does technology play a role in this? Well, three main ways. When we looked at all the fields that we had studied, we said, what are the three things that, technology-wise, that lead to new hydrocarbons? First one is reservoir visualization. So it's allowing us to do a better job. And this is a partial list. A lot of it's seismic-based. I'm not going to read through all these, but a lot of it is also logging, and something that's very new that I think is going to lead to a lot of new opportunities is fiber optics. And hopefully we'll have a fiber optics talk not too far in the future. That's one of the things. So, excuse me, any technology that allows us to better visualize reservoir. The second kind of group of technologies that has improved hydrocarbon recoveries in mature fields is our drilling and completion technologies. And I think this is pretty obvious. We're able to steer more direct, put the wells exactly where we want them, and then we have massive stimulations that allow us to produce from rocks that we couldn't do otherwise. Now, that's what's driven the unconventionals. Also, the deep water, some of this targeted drilling has really allowed that to be economic in many cases. And when you think about tight rocks, don't just think about unconventionals. There's a whole spectrum of rocks that are tighter than we originally considered to be productive that could benefit from stimulations. The final kind of thing that we saw, a way that people added hydrocarbons to the fields, was operational improvements. And bunch of things listed here. One of the biggest ones is artificial lift, so you can produce more water or produce at very low rates. The other thing, improvements in facilities, and I put kind of our secondary and tertiary recovery processes, IOR and EOR, in this category. Okay, getting back to that third element that I talked about, so reservoir characterization, kind of better applying new technologies. And then the one that's kind of really critical but hard to document fully is innovative thinking. So if you do tackle a field the same way it's been done in the past, exactly the same way, exactly the same ideas, you're not going to do anything there. So you've got to think about it either with new data or something, new ideas to find additional hydrocarbons. So I just listed a variety of things that we can do in here, from improved reservoir management, cost reductions that allow us to go for smaller targets, incremental efficiencies, and financing that can be creative. And I won't, again, to keep us closer to being on time, kind of keep that short, okay? Clay, you want me to wrap this up a little bit here? I can finish it up here a little bit early. I have a little bit more, but I'll wrap it up a little quick.
No, we're good on time. So yeah,
okay.
you can finish with this and
okay.
and go ahead and go to the end, and then we'll do some questions.
Yep. So what I've got here is an example of Forties Field in the North Sea again, and this is from our new paper that's coming out, and looking at this, and this work was done by Apache, a lot of it. So this was a very well-developed field by BP. It's one of their hallmarks. It made the company. Several billion barrels of oil were produced. They put in early water injection, and by good reservoir practices, extended the life 10 years beyond what they originally imagined. So kind of going through in the phases here, a couple things that are important to point out. This is time, increasing time from the initial field that put on production, and then this is the rates in 1,000 barrels of oil equivalent per day in green. The blue is the water production, and then another key thing to point out is this black line. This is the well count over time, okay? So we'll talk about both of these. So in the early phase of development, they started with phase 1, which is kind of the ramp-up phase. Kind of went into a period where they didn't drill as actively into phase 2 and started to let the field decline naturally without doing a whole lot. Water cuts started going up, but we still started producing at a fairly good rate, adding some wells as needed. They went into kind of the stage 3 of development, and what you're seeing here is a rapid decline in oil production, and water production staying relatively constant, which means our water cut is going up quite dramatically. You see they didn't drill any wells during that time frame, and that was also a time of difficult price. They went into stage 4 where they added artificial lift, and that allowed them to produce more water, which meant they can produce more oil. And so you can see that the production rate for the oil is, the decline rate, slowed down, but our water production has gone up dramatically. Okay. And you got to produce a lot of water if you want to get real high recoveries of oil. Okay. And so we get into the final stage, stage 5. It's very low activity, and you can see that the rates of production are fairly low, and you might think, okay, well, that's the end of the life of the field. There was still some reserves, and it's just going to decline out. They sold it to somebody smaller, and for a big company, it might be hard to justify developing that. If you have other opportunities that are bigger. So they sold it to somebody who was smaller. And what they did is all the things that we kind of mentioned. Development of bypass pay zones was critical, infill drilling. They used technology, 4D seismic, operational improvements, and a lot of creative solutions to do water lift. And we'll just kind of look at this real quick. So here's what I want to get to, and this is not uncommon. This is going from stage 5 till December of 2019 is when I pulled this data down. And you can see that when it's basically almost at abandonment or near abandonment, even though the blip in production is relatively small, by actively pursuing and working on this field, you can see they added a lot of wells. Each well produces a lot less oil than they did originally. But this right here, and it's still going strong, it's 300 million barrels of oil have been added, and that's actually by a significant number, especially if you do it in several fields. Okay. Just a couple of quick examples. Now, I want to make sure it's clear, BP did a great job developing this field, okay? And what they developed was the best reservoirs, and the field produced during their time more than 2 billion barrels. Here's the big massive sands. These are turbidites, and this is kind of a turbidite channel, and this is the boundaries of it. And the targets were these massive sands, and they developed those. But these thin things they call wings, which are kind of in the overbanks of the channel systems, are very thin. They don't really show up as conventional pay on logs. But the first thing they did is just recomplete a bunch of wells. They did drill wells directly for it too, and added a significant amount of hydrocarbons early on in the redevelopment just by recompleting those wells. And it has very, very good economics because, well, you know, you don't have to drill only well. Okay? They use direct hydrocarbon indicators, essentially just seeing where the field wasn't very well drained, and they added new development locations there. And here's where they really used some really advanced technologies. They did a series of 4D seismic data, and allowed to improve visualization. So the original reservoir model, which is what I would have guessed too, was that you have these turbidite channel sands, which are the big producers in the field. They're massive. The core looks pretty massive as well. I mean, there's variations, but nothing big. They assumed these had good continuity. They did a peripheral water flood early on in life of the field. But what they found out actually with the 4D seismic is that they were a lot more complicated than they realized. Okay. So what we're seeing here in figure B is a 4D image. The orange color here is what's hydrocarbon bearing and productive, and what's in blue is what has gone from hydrocarbon bearing to water bearing. And what you can see is that you've divided up some boundaries here, and they came up with the interpretation that these are actually 4 separate compartments that are poorly mitigated, and they map these things out. And I've kind of put in this dashed line to separate D because it was a boundary that created a lot of opportunities. And this is a kind of the red line is the line of section here. And what we see then is that on that map, the brown color represents areas where the oil has been produced or gone to high water cut based on 4D seismic. The blue are zones that have remaining hydrocarbon potential. And so the green are the producers during the period of the 4D seismic. And the yellow circles are new drilling opportunities. And so they see oil that was left behind. And so by doing 4D seismic here, this is a blow up of what we were just looking at. Green dots are producers. Blue dots are water injectors. And then the yellow dots were infill targets that were looking for kind of new opportunities. So undrained little pockets of oil in this massive reservoir. Kind of going through, this is the next 4D seismic. You can see the areas that they targeted were produced, but they found that oil was moving through the reservoir in a kind of less complete method. The yellow dots, again, are targets of oil that's moving through non-uniform in the reservoir. They targeted that with additional wells. Now, kind of to do that 4D takes high oil price, okay? But the other things don't. So kind of the highlights here, this is the field that was originally going to be abandoned in like, 1990 or sorry, 2000. It's going to, went from 140 million BOE when they identified it for reserves. Looking at the spin-bitted pays and such, they added about 800 million BOE in the field, brought production up. Anyway, still producing strong. It's already produced 300. Plus, they found a lot of small fields nearby that they've added to the production, and they expect it to last to 2030. Okay, so just kind of giving them a long kind of lived on that. What did they do? Bypass pays, infill drilling, and they did some things I didn't talk about with improved operations. Okay. So let me just kind of wrap that up a little bit, keep us closer on time. So searching for hydrocarbons is, to me, in old fields is a reliable way to add reserves. And right now, in times of economic stress, some of the advantages are that we own the assets already. We may own the assets. And so adding these reserves is incremental, meaning we don't have to put a whole lot of capital at risk to add the hydrocarbons. So there's not, a long phase of exploration expenditures. And if we're acquiring assets, if we have the funding, it's a cheaper time to acquire assets. How do we do it? Well, we talked about the three elements that we see in all kind of big reserve additions: better characterization or understanding the reservoir, applying technology, and being creative in how we do that. One of the things that I mentioned, but I want to emphasize, because it's one of the more important things, is economics is the key, whether or not this can work, and you have to be very prudent on how you do this. So bypass pays, that's have great economics generally. When we look at the interconnectivity, which is also a place of lots of opportunities, both structural and stratigraphic, you still have to put capital expenditures in, and so the economics aren't as good. Same thing with the external geometry, looking at the satellite discoveries near a field. Those find hydrocarbons, they're usually smaller than what we found in the original development, and you have to drill well, so it can make money, but it depends upon the price of oil. Okay. So technology can be expensive, so if you're going to use it, you have to apply it where you have the best chance of success. Don't recommend that you do it just randomly without a good lot of thought in there. Okay. So again, I think history suggests there's lots of opportunities for people who are enterprising, willing to be diligent, apply technology, and be creative. And that's what I had to say. Thank you.
All right, thanks, John. We've got a couple questions that came in during the presentation, so I will run through those. But if there are other questions, we still have a few minutes here, so feel free to type those into the chat, and I will give them to John. The first question here asks, can you elaborate on how borehole seismic improves reservoir visualization?
Yeah, so a lot of it depends. So what the borehole seismic can do essentially is, particularly if you have subsalt or things like that, just gives you higher resolution, higher frequency data. So basically you're just getting slightly better visualization of the reservoir than you can do with the subsurface. Based on frequency content, and then if you have anything that blocks your signal. And that's a kind of short answer. I'm not an expert in seismic visualization. So. Okay.
The next question here came in when you were on the innovative thinking slide, and asks, what are examples of cost-reducing initiatives?
Well, I'll give you one that just on the Forties example that we did, that we looked at, which was kind of how do you get costs. One of the biggest problems, and again, because of time I couldn't talk about it all, is, paying for water lift. And in oil fields, if you're going to produce a lot of hydrocarbons, you have to produce a lot of water and it costs money. And one of the problems they had in the Forties Field, for example, was lifting costs, and they were using diesel, and they were bringing diesel out to the platform and doing it, and they could only store so much. North Sea has bad weather. So one of the things they did there, just as that cost is they actually drilled shallow gas hazards. And so that was pretty cheap to do. They hooked it up to the rig and saved massive amounts of money, have unlimited energy supply. So that's kind of that's a quick thing that came to my mind. But so just being creative and things like that. That's one example.
Okay, and then the last question that I've got here, but again, if you still have any remaining questions, feel free to type them in, asks that we talked a lot about mature fields in this presentation, but what about less mature fields or newer exploration?
That's a very good question, and so one of the things that we looked at when we're reviewing a lot of these fields is that by looking at kind of these processes and what we've learned over time, the way you apply this kind of concept in new fields and new discoveries is basically compressing the time it takes to produce the field. I had another example in here from Oman if we had enough time, and so kind of the steps we go through in the characterization are the same, but what we saw is that newer fields learn from this process, and you're basically compressing the timeline to doing these things. So you start doing bypass pays earlier, you start doing any kind of monitoring earlier, and you greatly increase the economics of your new field. Okay. And we're seeing that trend in big fields is what we just finished studying, but fields aren't economic if they take too long. If you compress the time frame, that's basically how it works.